This presentation will talk about the behavior of real gases. Our lesson objectives will describe the physical factors that lead to deviations from ideal gas behavior. We'll explain these factors are represented in the van der Waals equation. We'll define compressibility, known as Z, and describe how its variation with pressure reflects non-ideal behavior. And finally, we'll quantify non-ideal behavior by comparing computations of gas properties using the ideal gas law and the van der Waals equation. Gases in real life do not always behave ideally. Shocking, I know. When a gas is behaving ideally, we can describe it using the ideal gas law. So we remember that PV equals nRT. And if we put all of our variables on one side, we get 1. If PV equals nRT is not equal to 1, we say the gas is not behaving ideally. We can also make an alternative comparison and use molar volume of a real gas versus molar volume of a that we would predict from the ideal gas in a ratio known as compressibility. We give it as the letter Z. This is not to be confused with the atomic number Z. They are entirely different things. Z, when talking about atoms and isotopes, is the atomic number, and Z, when talking about ideal gases, is compressibility. Anyway, if we take the ratio of the molar volume of a real gas to the molar volume of an ideal gas, or what it would be predicted, the 22.4, we get a ratio of P times molar volume over RT that we measure. So in other words, this is our deviation from 1. It will be given by Z. Okay, so if we plot our Z value, our compressibility, which is PV over nRT in real life, we can see that we deviate from ideal gas behavior a lot of the time on this particular graph. This deviation starts to happen as we increase pressure. At low pressures, all of the gases are behaving ideally, where Z is equal to 1. As the pressure gets higher, the deviation increases. But why does this happen? Ideal gases follow the postulates of kinetic molecular theory. A real gas will deviate on certain postulates. Generally, at room temperature and pressure, a gas will behave ideally. If we keep volume constant, if pressure increases, the volume of the gas molecules relative to empty space decreases. So in other words, we've added more moles of stuff and the molecules are closer together. So as that ratio decreases, at a certain point we can no longer approximate the volume of the gas as being equal to zero. Therefore, we no longer follow postulate 1. So it turns out in a real gas, molecules do in fact have volume. So we get this deviation when the pressure is high and the molecules are very close together. If we keep volume constant and lower pressure, the gas molecules start interacting. Our ideal gas says that we do not attract or repel, but we know that real gases may attract or repel. So gas molecules can attract or repel when they're close enough together. This causes the molecules that are attracted to each other to have a smaller pressure and the molecules that repel each other to have a higher pressure. If the pressure is held constant, molecules that attract each other will decrease in volume, and if they repel each other, they will increase in volume. Generally, they will all be attracted, and they will decrease in volume. The fifth postulate breaks down at high pressures. Another way that these postulates fail is when the temperature is very low. So at high temperatures, the interaction between colliding molecules is really brief. This prevents the molecules from interacting, so the fifth postulate holds. But at low temperatures, the approach speed is greatly reduced, and the molecules have time to feel the effect of their proximity. So at low temperatures, postulate 5 fails. There are quite a few theories that predict how a gas will deviate from ideal behavior. We'll learn about the first and simplest version, the van der Waals equation. Van der Waals postulated that at high pressures, gases have a significant volume. So he created a term to subtract the volume of the gas from the overall volume of the container it is in, minus NB, where N is moles and B is a virial coefficient. Real gases also experience attractive and repulsive forces, which van der Waals knew. So he made a term, N squared A over V squared, to represent those forces. The closer the molecules are together, the more and greater the attractive and repulsive forces. So the more pressure will deviate. Both A and B are empirically determined. So just for the record, empirically determined means you got it from data. Someone did a series of experiments to find the values. So let's try using this equation. Now, it probably is a good idea when you do these calculations to go ahead and write out your variables and what they're equal to before you plug them in. In this case, I'm just going to YOLO it, so let me know if I've messed up. We're going to calculate the pressure of 1 mole of nitrogen at 500 Kelvin and a volume of 2.5 liters. All right, so I plugged in my variables, including the virial coefficients that I got from the table in the book. And now I'm going to try to solve this, but I like to solve it in parts because I tend to type equations like this into my calculator incorrectly. The struggle is real. Anyway, I go ahead and I do that, and I start solving little parts of it, use my algebra, and eventually I get the pressure is equal to 16.2 atmospheres. An ideal gas would have had a pressure of 16.42, so this is in fact a lower pressure than you would expect. Okay, to summarize, when PV over nRT is unequal to 1, the gas is behaving non-ideally. We can describe this using the compressibility factor. So PV over nRT measured is Z. Ideal gases have no volume, and they do not attract or repel, but real gases have volume, and they do have attractive or repulsive forces. The easiest and, well, the simplest and first equation to deal with real gases versus ideal gases is the van der Waals equation given here. A and B are virial coefficients, which are empirically determined.